Chapter 2, Introduction to Optim. Actually, in this chapter, we are going to talk about fitting of nonlinear models, and the function Optim is meant for that. So here, Optim has the argument par, that is the parameter of guess values, then fn, the objective function, then Hessian is equal to true. And this Hessian is equal to true means it will return Hessian matrix also. Is meant for, this Optim is meant for nonlinear unconstrained optimization, preferably minimization. It requires guess value of the parameter, argument par, objective of the objective function, and that is nothing but minus L theta. L theta is log likelihood, negative of log likelihood of theta. The argument Hessian is equal to true is required to return Hessian matrix at the optimum point. 3 dots at the end of the argument stands for arguments which are not specified. See, suppose we want to fit exponential model. So fitting of exponential model, note that here fy is equal to lambda into e raised power minus lambda. That is nothing but dexp y rate is equal to lambda. This implies that the log likelihood for the exponential with rate lambda is equal to Li log of this, and log of the above function then is equal to log of lambda minus lambda yi, because e raised power minus log of e raised power minus lambda y is nothing but minus lambda y, and this implies L lambda is equal to summation of Li, and that is nothing but sum dexp y lambda log is equal to true. So actually what we need the first thing is that our function is fx is equal to lambda into e raised power minus lambda y. So this is a function of both lambda and x. When it is treated as a function of lambda, it will be termed as likelihood function. When it is treated as a function of x, it will be joint density function. When it is treated as a function of lambda, it will be likelihood function. So actually in maximum likelihood estimation, what we need? We need first likelihood function, then we try to maximize likelihood function with respect to the parameters. So, and that is known as likelihood estimator. So here we have defined this log likelihood and then log likelihood, and of course maximization of likelihood is equivalent to maximization of log likelihood, because logarithm is the monotonic function. So here we shall fit, first we are setting set.seed, y is equal to rexp, rate is equal to 0.03, simulate 20 random observations from exponential distribution, and see these are the 20 observations from exponential distribution. Then we are going to define a function, define negative of log likelihood of exponential distribution, NLLE, negative of log likelihood of exponential, with function, the first argument of the function is theta, another one is y, that is data. So LL is equal to DEXP y rate is equal to theta and log is equal to true. Log we are writing because we want log likelihood. So basically this log is required because we need log of these values, we need log of this. So this job will be done by writing log is equal to true. So that's why we are writing log is equal to true. And then it will be a vector, and then we are writing LL is equal to sum LL and then return minus LL. Return minus LL because we want negative value of the likelihood function should be returned. And we know that say this is L theta, so max with respect to theta is equal to min of minus L theta. So it is a well known result because Optim by default it minimizes, so that's why we are returning negative values. And then we are dumping this function, and then we are going to call M1 Optim. Par is equal to par, the first argument 0.01 is the value to start the iteration. Fn is equal to the objective function. The objective function is NLLE, this one. And Hessian is equal to true. It will return Hessian matrix. You know what is Hessian matrix? Hessian matrix is nothing but, L theta is L dash theta is the Jacobian, first order partial derivative, and L double dash theta is the Hessian matrix at the optimum point, at the observed optimum point. So minus L theta hat, this is known as Hessian matrix, and if we make negative of the Hessian matrix, it becomes Fisher's observed information matrix. It becomes Fisher's observed information matrix. Fisher's observed information matrix. Because there is a result in maximum likelihood estimation that theta, there are certain properties of maximum likelihood estimator. One is that it is always a function of sufficient statistic, then it is efficient, it is consistent. The most important property is that asymptotically its distribution follows normal distribution. So theta hat converges in law or in distribution to normal theta, and its variance, it is normal distribution with variance I, Fisher's information matrix. This is known as asymptotic variance of theta. This is the mean of the theta hat, and this is the asymptotic variance. So to get this, we need negative of the Hessian matrix. We have already made negative of the function to return. So we just need second order partial derivative, and that is nothing but Hessian is equal to true. So with this Hessian is equal to true, we are getting this thing. And then method is equal to LBFGSB. LBFGSB, actually it is, there are many options. If you go into the help, Optim, see here, help Optim. See here, Optim, this is the method. Method is equal to, see the details, method is BFGS and then LBFGS. LBFGS. Actually, BFGS is the name of the four authors which developed this optimization method in 1970s, and all of the four authors, the BFGF stands for the first name of the authors, like B stands for Brody, F stands for Fright, and then G stands for Gottfried, and S stands for Shanno. So these four authors communicated independently, and they they recommended this software. And this LBFGS is the constraint estimation. It provides certain constraint, and that's why we are giving here LBFGS B. So lower is equal to, so we have to put lower bound, because for lambda we put a restriction that lambda is greater than 0. So to put this restriction, we are writing lower is equal to 0.001. And why? Because par, we are doing optimization with respect to the par, and that means that is the value of theta. But y remains there, so y we have to provide y is equal to y. And then see, this is the output par. Par means it is the optimum value. We have started iteration from 0, 1, and optimum value is 0.027. So this is nothing but lambda hat ML estimator 0.027, and this is the value. Value means the value of the objective function, and that is nothing but L theta hat minus L theta hat, and that is equal to 91.842. So this is the value of L theta hat. Then convergence 0 means successful convergence, and then Hessian matrix. See, this is the nothing but minus L double dash lambda hat or theta hat. So this is known as Hessian matrix. It is 1 by 1 matrix because we are having only one parameter. Then what we are doing, we actually extracting from this M1, because M1 is the fitted object, we are extracting par. We are extracting this value par, and that is nothing but ML estimator. And to get the standard error, what we have to do, standard error is nothing but it is diagonal, because this solve is nothing but I inverse. This is the Hessian matrix, negative of the Hessian matrix, and solve means inverse of the negative of the Hessian matrix. And then we are extracting its diagonals, and then we are making a square root of those, because these diagonal elements, they are variances. So we are extracting diagonal elements, and then we are making a square root of those. So this is known as standard error. So this is the standard error of the 0.027 estimate. And see, this is the standard error. MLE is 0.027 and standard error is 0.006. Now what we can do, we can use out is equal to R bind, row wise binding of MLE and SC. So it is row wise binding. Column name is rate, the name of the parameter. So it has row bound MLE, SC, these are the row names, and then column names is rate. So this is the MLE estimator, this is standard error. So this way we can get all the results. And suppose we want to do these things, here what we have to do, here we have to see all these theories are given here. So first we are getting this is set.seed, so that we should generate the same set of observations. Then y is equal to, this is the y, and then we can print y. These are the 20 random observations from exponential distribution with rate is equal to 0.03. And then we are going to define the function, the objective function to be maximized. So that is NLLE is equal to C. This is the objective function to be, and it returns negative of log likelihood. So that means it is returning negative of log likelihood, which is our requirement. And then we are dumping the function, so that, and we can source it using the function source, which we are not writing here, but we can go source. It is n, in double quotes we have to write nlle dot txt. NLLE. Oh, we have not dumped this. First we have to dump. NLLE, and file name is equal to nlle dot txt. So we have dumped this. Now we can source it. nlle.txt, nlle.txt, Now we can see whether, yes, it is there, it has been dumped, and the file is nlle.txt, and then we can dump, dump. Then in double quotes we have to write nlle and file is equal to nlle.txt. And now we can source nlle.txt. So it is sourcing now. So dump and source we have already talked. So we have dumped it, and then we can source it. Then we are going to fit this. For fitting, the function is Optim, and this is the par is equal to 0.01. So this is the guess value to start the iteration. Then fn is the objective function to be minimized, and nlle is the name of the function. Hessian is equal to true, it will return the Hessian matrix also, and then method is equal to L dash BFGS dash B, and lower bound is 0.001 and y is equal to y. So when we will run this, it has been run, and we can print the results. These are the results, and then I've already made interpretation of all these things. Now, how can we go for fitting a Weibull distribution? Because fitting a Weibull distribution is quite complex. So, I am going to fit Weibull distribution using Optim. Fitting Weibull distribution. Weibull is a very popular distribution for fitting of reliability and survival data. It has shape and scale parameters. It is fitted as, actually, Weibull distribution is very popular distribution. There is a great package in R, in base R, that is survival. In survival, we study survival analysis, and in survival analysis very typical models are seen. So to fit those models, if we don't know about the model, which model should fit, there is a default choice, and that choice is that of Weibull distribution. Weibull is so popular. Weibull was introduced by Weibull in 1951, and he introduced to study the strength of the chalks. And after that, it became a very popular model among the statisticians, among reliability analysts, among survival analysts, among so many other fields too. It is very popular. So, Weibull model, we can just look into Weibull distribution. Help D Weibull. See, D Weibull, it has the Weibull distribution. It is D Weibull, it is value of the density, and then P Weibull, value of the CDF, then Q Weibull, value of the quantile, and then R Weibull, value of the simulation, value of the random simulation. So these values are returned. Now see, so we have written here y is equal to R Weibull, 30 observations, shape is equal to 1.5, scale is equal to, see, just Weibull is an extension of the exponential distribution. In the case of exponential, fx CDF is equal to 1 minus e raised power minus lambda. Fx is equal to 1 minus e raised power minus lambda x. And if we define in terms of, this is in terms of rate, if we define in terms of scale, it will be e raised power minus x by theta. So theta is nothing but scale parameter, and lambda is the rate parameter. So there is a relation between scale and rate. So rate is equal to 1 by scale. So exponential distribution has been defined in terms of rates, whereas Weibull distribution has been defined in terms of scale. So the distribution of Weibull, W Weibull, can be written as 1 minus e raised power minus x by theta whole raised power p. So here p is the parameter scale. P is equal to shape. It is not scale, it is shape. P is equal to shape. P is equal to shape. So it decides shape of the distribution. For p is equal to 1, it becomes exponential distribution. But for p, normally p is greater than 0. So here we have taken shape is equal to R Weibull, 30 observations are being simulated. Shape is equal to 1.5 and scale is equal to 50. Simulate 30 observations and define the log likelihood, define the negative of log likelihood of Weibull, that is L theta. Theta is equal to shape comma scale. So n LLW, negative of log likelihood of Weibull distribution, is equal to function of theta and y data. And then LL is equal to d Weibull, y, shape is equal to theta 1, scale is equal to theta 2, log is equal to true. So here what it does, it computes the value of the log likelihood at each data point y, and shape is equal to theta 1 and scale is equal to theta 2 because we have defined in terms of theta. So log LL is equal to sum LL and return minus LL. Then we can dump this function NLLW and we can source it using the source NLL source and make this text file name. Now to fit this, we have to use Optim. For fitting Optim, par is equal to the guess value of the shape parameter that we are taking 1 and 30 we are having the guess value, although we know exactly it is 50, but here we are giving the guess value 30 to start the iteration. Then Fn is equal to, this is the objective function to be minimized, that is NLLW, which is defined here, and Hessian is equal to true, method is equal to LBFGSB, and lower is equal to 0.1 for, 0.1 is the lower point for the value of shape and 2 is the value of scale, because we know for here P is greater than 0 and theta scale is also greater than 0. So we have to put this restriction here and we are going to put this lower is equal to 0.1, it is greater than 0 and 2 for the theta, and it will optimize, and it is optimizing. Hessian is equal to true, it will return the Hessian matrix, and then method is equal to LBFGS. This is the lower bound, so that it will optimize after this 0.1 and 2 only. It will not go into the negative values. Then MLE M2 par, this is the MLE of the, this is the M2 par, that is we are extracting from the fitted object M2 the value of the maximum likelihood estimator. Then to estimate standard error, SQRT, diag, solve M2 $Hessian. This is the Hessian matrix which is being reported by the Optim function, and its negative is already there because we are optimizing this negative of log likelihood. So there is no need of making it information matrix as negative. Then solve inverse of this matrix, and then we are extracting diagonal elements, and then we are, because diagonal are variances and their square root is nothing but the standard error. Then out R bind MLE SC, R bind out is equal to R bind MLE SC. Call names out, shape and scale. So these are the column names. And see, these are the results. MLE, we have started simulation with shape is equal to 1.5. So it is optimum value is, maximum likelihood estimator is 1.48 and scale is 48. It is scale is 50. Scale is 50. We have simulated scale with scale 50 and its maximum likelihood estimator is 48.16. And its standard error of the shape parameter is 0.215 and that of scale parameter is 6.20. So it may be noted that fitted values are in close agreement with the true values, which shows the strength of fitting procedure. Now in my next lecture, I shall talk about describe this fitting of Weibull graphically. So I will show you how graphically you can check these estimates. We have to emit histogram of the simulated data and then we will try to fit on the simulated data. So this is the assignment, and then I am going to talk about fitting of nonlinear regression model with Optim. So that will be my next lecture.